but this is one important part. We need to attend the problem, and in subject 3, we'll be getting definitely we'll be getting a question from this chapter. Okay, sir. My PPT will not be so attractive. I just took many screenshots and added. I will just have a look at it, sir. Please kindly bear with me. Sir, mostly we'll be encountering induction motors only. Almost all the industries have induction motors with them. Very rare we may encounter with synchronous motors. So robust machine universally available motor is induction motor. So we'll be concentrating on induction motor only, finding efficiency of an induction motor. Speed and slip, all these things we know, but we'll have a look at it. What's that synchronous speed? Synchronous speed is 120 F by P. Otherwise, we usually call it as Pn by 120 is the frequency. To find the speed, we multiply with 120 into F by P. P is the number of poles. We cannot reduce less than 2. So lowest possible P is 2. In that case, F is 50, 120 into 50 divided by 2 will give us 3000 RPM. So the maximum available RPM in an induction motor is 3000 only. We cannot get more than 3000 RPM electrically. If we increase P, the speed will reduce. If it is a 4-pole machine, then the speed will be 1500 RPM. All these speeds are commercially available in the market, sir. Slip is this definition we have to keep in mind, sir. If you have forgotten, please recall. This is synchronous speed minus full load rated speed divided by synchronous speed. That is ns minus n divided by ns. It is called slip. Everywhere we will be using that slip, sir. We will be getting problems inclusive of slip. So we will be using everywhere the slip. So please keep in mind what is slip. Slip is synchronous speed minus full load rated speed divided by synchronous speed. Otherwise, we can simplify as 1 minus full load speed by synchronous speed. Both are same. Okay, sir. We will see some useful points. Squirrel cage motors are more efficient than slip ring motors. Higher speed motors are normally more efficient than lower speed motors. These are all facts, are just keep it in mind. The efficiency is a function of motor temperature. Yes. TEFC, totally enclosed fan coat, are more efficient than screen protected drip proof motors. Both these types we will I'll share the next part of this program, this chapter, sir. We'll just rush up. Totally enclosed is it will have less windage losses. That's why it is more efficient. Motor efficiency increases with the rated capacity. These are all universal truth. What are fixed losses? Fixed losses means whether the motor runs on no load or full load or off load, whatever it may be, these losses will be constantly uh, uh, incurred in a motor. For example, magnetic core loss. Magnetic core loss is of two components. One is eddy current and hysteresis. Hysteresis loss is nothing but magnetizing, demagnetizing, and it will be the magnetizing and demagnetizing will be happening for every cycle of the alternating current, sir. It is the magnetic poles will align themselves, de-align themselves, and all these things, internal structure. There will be friction at the molecular level and heat will be generated. This is called hysteresis. Just have an idea. That's all. Eddy current means the magnetic flux, change in magnetic flux, cuts the conductor and produces electricity. The same thing happens to the body of the motor also. The body of the motor is also made up of a conducting material. We cannot make it a non-conducting material because all the magnetizing materials are conducting materials only. So whenever there is a change in magnetic field, it not only induces electricity EMF in the copper conductor, it will also induce voltage in the magnetizing material, thereby producing current. That's why we are making in laminated sheets. Laminated sheets will increase the resistance of the magnetic path so that the current flow will be reduced. EMF induced divided by the resistance will give us the eddy current. So by lamination, we are increasing R. All these things, hysteresis loss and eddy current loss, both are fixed losses. Irrespective of the load, this will be happening. Magnetic losses vary with core material and geometry and with input voltage. What is the geometry? Just we saw that lamination makes it lesser. Magnetic losses, the core material. Core material means nowadays we are making energy efficient motors with core material. That core material are excellent in magnetizing properties, whereas they have high resistance also. Friction and windage losses. We know all these things. Friction means friction happens in the bearings. Windage losses means there will be fan circulating inside the fan will be provided in the end of the motor and it will be circulating air through the rotor and stator coils so that the I square R loss is dissipated. But that fan, due to damping in the air, will incur some losses, that is called windage loss. Friction, windage losses, losses in bearings, aerodynamics losses associated with ventilating fan and other rotating. Just now we saw. What are the variable losses? Resistance losses in stator and rotor and miscellaneous stray losses. Why we call it as miscellaneous stray losses? That cannot be accounted, but that is proportional to the current, sir. We see one typical curve. You can see that the efficiency is not always here, as we think. It is not always highest in the rated load. See, sir. In this curve, efficiency occurs at 50% of the load because there will be a compromise I square R loss plus ion and friction losses. All these things will come together and they will define and they will give us a curve which will not be always. We may not get the maximum efficiency at full load. And power factor, the power factor is we can draw this cursor power factor from no load. It will be very, very low, and the power factor will be improving with increase in load. Even at 150% of 1.5 times of the rated power output, the power factor is maximum at that particular load. So it increases with increase in load. Power factor. Please keep this in mind, sir. Power factor increases, whereas efficiency increases in course, and after 50% of load, it slightly reduces. But before 50, it steeply comes down. At 20% and 20% and all, the efficiency will be very, very low. Load power factors at various speeds. This thing we just saw. See, 0.9 power factor occurs at the synchronous speed, 3000 RPM. Sorry, before we saw power factor with load. Here it is power factor with speed, synchronous speed. See, it is very low at 375 RPM and it is very high at 3000 RPM. Okay, sir. What is efficiency? Efficiency is nothing but the output power divided by the input power. Output, we can write it as input minus losses. Input minus losses. So we can write it as P out as P in minus P losses. The first term P in by P in will become 1. The second term P out by P losses by P in will come here. Okay, sir. 1 minus P loss by P in. When the loss becomes 0, efficiency will be 100%. Okay, sir. The loss is a percentage of input, sir. F and W and core losses. F and W and core losses are friction and windage losses and core losses. Sir, C, no load power. No load power, what is that no load power? The motor is run without any coupling. The rotor will be rotating, but the rotor will not have any mechanical coupling. So it is running on no load. In that case, what the stator draws, that is no load current. No load current square into stator resistance will give us the total no load power minus stator I square R loss will give us friction and windage and core losses. Right, sir? Okay, sir. Is there any doubt in this formula, sir? We'll be using this in problems. So, please pay attention to this formula. What is that friction and windage losses? No load power minus stator no load I square R loss. Okay, sir. Sir, temperature correction, we have to do it. Temperature correction. The resistance will not be same when the motor is at room temperature. That is, before starting, the resistance will be very low. After running, at full load, the temperature will be rising, and this rise in temperature will change the resistance. Resistance is not constant always. Resistance varies with the temperature. Positive temperature resistance coefficient, you must have studied in our college days. See, R2 by R1 is equal to 235 plus T2 divided by 235 plus T1. What are sir, one more point, sir, rotor I square R loss. It's an indirect measurement, sir, rotor I square R loss. This is stator input. minus stator I square R loss minus core loss. So what is this? Stator input, stator I square R loss, stator I square R loss, and core loss. We have to subtract these two from the stator input and multiply it with the slip. It will give rotor I square R loss. This is an indirect method, sir. Once again, I am giving this formula. So we have to keep it in mind. What is slip? It is ns minus n divided by ns. Synchronous speed minus full load rated speed divided by synchronous speed. So the stray losses, we are taking it as for granted. We cannot measure it, sir. We measure it indirectly only. For the lower HP motors, the loss will be higher, so stray losses. With increase in capacity, the stray losses gradually reduces. But we'll be facing LCN 120 HP motors only. So the stray losses will be around 1.8. So we may have to assume if the data is not given in the question. So please note down 120 up to 125 HP, the stray losses will be 1.8% only. Beyond that, 1.5. Okay, sir. Some points we have to keep in mind, sir. When purchasing large number of small motors or a large motor, large number of small motors or a large motor, as for the detailed test certificate, if possible, try to remain present during these tests. This will add cost. Where we are doing all these things, sir, for new projects, we'll be going for inspection in the project wing of TNLB, and we'll be asking the manufacturer to test all these things in front of us. Okay, sir. See, the efficiency values are specified without any tolerance. Check the actual input current if replacement is done. Yes, if there are any replacements, we have to check with the actual input current. For new motors, keep a record of no load input power and current. This has to be done before commissioning the motors. Use values of efficiency for comparison and for confirming. Rely on measured inputs for all calculations. Use values of efficiency for comparison. What they have given as efficiency in the nameplate, we can keep it for comparison, and for confirming, we have to rely on measured input for all calculations. Okay, sir? A, B, C, D, E. Estimation of efficiency in the field can be done as follows. Measure stator resistance and correct operating temperature. Yes, sir. Just we saw the correction formula. From rated speed and output, I square R loss can be calculated. From no load test core, friction and windage losses are determined for stray losses. We'll do one example, sir. This is a question, sir. Rated power is 34 kilowatt. See that in that particular tabular column, we saw huge motors, but in practice, we don't use the motors and all. We'll be using much smaller motors. It is only 34 kilowatt only. And they have given the horsepower rating also. The voltage is 415. What does it mean? It means it is a three-phase motor. Current is 57 amps. What is the current 57 amps, sir? It is the line current, sir. It will be in delta connection only, sir. Okay, and the line current will be more than the phase current. Phase current will be will have to be divided by root 3. We have to divide it with the line current by root 3. Speed is 1475 RPM. Sir, in this case, what is NS, sir? Can you say, please, what is NS synchronous speed?
Mm-hmm. 1500.
Yes, sir. Yes, sir. Exactly. Insulation classes have frame and all. They are given. Yes, sir. We have got that connection also, delta connection. Okay. No load test. No load test is we get 415 volt. Current is 16.1 amps. Please keep in mind because we'll be moving to other slide and we will not be able to see this. 1475 RPM is the rated speed. Rated current is for 57 amps and no load current is 16.1. 57 and 16.1. See the difference, sir. Stator phase resistance at 30 degrees. That is the temperature. Room temperature, the phase current is stator phase resistance is 0.264 ohms. No, the no load power they are given straight away is 1063.74 watts. Yes, we'll go to next slide, sir. What they are asking, first one is calculate iron plus friction losses. Iron plus friction and windage losses. Calculate stator resistance at 120 degree. They have given the formula itself. That, but in the examination, they may not give the formula. We have to keep in mind. Okay, sir. Calculate stator copper loss at operating temperature of resistance at 120 degree. So 120 degree, we have to calculate the resistance. Calculate full load slip and rotor input, assuming rotor losses are slip times the rotor input. We saw one formula, sir. So we will be using it. Determine the motor input, assuming the stray losses are 0.5% of the motor rated power. Calculate motor full load efficiency and full load power factor. Okay, we go into the problem. Yes, sir. Sir, do you remember they are given P suffix NL? P suffix NL means it is no load power, which they are given straight away, that is 1063.74. What does it include? It includes no load power is equal to stator copper loss with no load current, sir. 3 into 16.1 is the line current. As I already told you, it is a delta current and delta connection. For delta connections, we have to divide the line current with root 3. Right, sir? This is between this bracket, it is phase current. Phase current square into phase resistance. This must be multiplied with 3. There are 3 phases, so we have to multiply it. Sir, just a minute, sir. I'm gonna charge this. Okay, sir. The power input, that is iron loss plus friction windage loss is equal to no load power input minus no load copper loss stator. Sir, is it easy to apprehend, sir? What is no load? No load is the shaft is without any load. The motor draws some current and the power input is for one iron loss, that is fixed, and friction and windage loss, that is also fixed. And what is that? Stator copper loss. Okay, sir. All these things come together. So we have to add all these things from the no load power loss they have given in the data itself. That is 1063.74 minus the copper loss. The copper loss we just found in the previous step, sir. 68.43 we have found. So 1063.74 minus 68.43 gives us 993.3 watts. This is what, sir? Iron and windage loss. Okay, sir. Okay.
Okay.
Now, the stator loss. Previously, we found the stator loss for no load, and it was for the room temperature. Now the resistance will be increased at 120 degrees centigrade. So we have to correct the factor. Positive temperature coefficient, sir. Positive temperature coefficient means what? Resistance increases with increase in temperature. The numerator will be having that particular higher temperature, and denominator will be having that room temperature. Okay, sir. So what we get? 354 ohms per phase. Stator copper losses at full load. The same thing. What is the change, sir? We find that the stator current changes from that 16.1 into 57. But the root 3 and all remain the same. At the same time, the R also becomes 0.25 something, sir. What is that? What was that? Sorry, 0.264. Sorry, 0.264. Now it has become 0.354. What is the present loss? This is now it is 1150 watts. Okay, sir. What is that full load slip? Slip we can find it easily, sir. 1500 minus 1478 divided by 1500. NS minus N divided by NS. The slip will be always in fractions, sir. 0.0167. It has no units at all, sir, because the numerator is in RPM, the denominator is also in RPM, so it will be a mere number. Okay, sir. What is the rotor input? The rotor input is equal to, so this one we are calculating indirectly, sir. So please concentrate at this point. PR rotor input is equal to output of the shaft. Output of the shaft divided by 1 minus S. Just to keep in mind, divided by 1 minus S. We'll go back to the data, given data. Rated power. See that first points are 34 kilowatt. They are using it. 34,000 watts. Sir, what is this, sir? Can anyone refresh it now, sir? What is that? 34,000 watts. What is it, sir? What is that power, please? Sir, please. What is that 34,000?
Sir, 34 kilowatts, sir.
What is that power, sir? Where it is available?
Available in this calculation 34,000 near we have to take in it 34 kilowatt.
No, sir. What is that output, sir?
What is the mechanical output, sir?
Yes,
Rotor
sir. Yes,
output
sir.
means
Yes, sir.
mechanical output.
Yes, sir. Yes, sir. Yes, sir. I just wanted to remind, sir, that's all. It is a shared power output. In
Yes,
the
sir.
nameplate itself, they have given 34 kilowatt motor, and we are once again cross-checking it. The rotor power output is equal to 34,000. We are using it in the calculation, so we will not forget hereafter, right, sir? That's why I am recalling it. Nothing else. 34,000 divided by 1 minus slip, we will get 34,577.4 watts. This is the rotor input, sir, not that stator input. It is the rotor input. Rotor input, we can indirectly calculate. We cannot measure it, sir. Rotor input, we cannot measure. So we are calculating it as 34577.4. This is an important problem, sir. This problem contains various steps which will be much useful in our exams. That's why I'm going very slowly. Motor full load input power. What is that motor full load input power? This is what is that P rotor? P rotor, just we saw, sir, P rotor and P stator copper loss at 120 degrees centigrade. Okay, sir. Rotor input. The rotor input is coming after all the losses in the stator. So rotor input plus the losses made in the stator for copper plus the iron loss plus the friction and windage loss plus that stray loss. Okay, sir. Any confusion? Is it okay? Is it clear? P rotor, we just found it. And P stator copper loss at 120 degrees centigrade. This also we have found already. And friction and iron loss plus friction and windage loss 995.3. We have found it already. And stray loss. Stray loss, this is the data given in the question. Okay, sir. 0.005 into 34,000, that is the motor output. So what we get? 36,892.8 watts. This is the motor full load input power. Yes, where stray loss is equal to 0.5. Oh, yes, sir. Yes, yes. Sir, please. This is my important point, sir. I thought they are given in the question itself, but they are not given. So we have to assume stray losses is equal to 0.5% of the rated output. Okay, sir. Motor efficiency at full load. Motor efficiency is equal to P output, shaft output divided by P input. P input is the input of, what is that, sir? That is the electrical power input. Okay, sir. Because we have added all those things. We have added all those things. So friction, voltage loss, everything we have added. Copper loss, everything added. So it is the 36,892.8 is the power drawn from the plug point. 34,000 is the mechanical power output available in the shaft. Okay, sir. So this gives us the efficiency, that is 92.2%. What is the full load power factor? Full load power factor is equal to, we know power is equal to root 3 VI cos phi. So power divided by root 3 VA will give us the power factor. Full load power factor means that is full load power input divided by root 3. 415 is the voltage. 57 is the full load current. So we get 0.9 as power factor. Okay, sir. We'll see the comments. The measurement of stray losses is very difficult and not practical even on test beds. So we take it as granted with some assumptions, or otherwise we use the data they are giving in the question itself. Mostly they will not make us assume everything, and also They will just give the data. Otherwise, sometimes actual value of stray losses of motor up to 200 HP is likely to be 1 to 3% compared to 0.5 assumed by standards. What does it mean, sir? Even if you assume it as 1% or 2%, so we'll get the full marks. No need to worry about all those things, but it should be realistic. We should not put it as 5% or 6%. So it should be realistic. The third point is the value of full load slip taken from the nameplate data is not accurate. Actual measurement under full load condition will give us better results. So stroboscopic measurement will give us the actual speed, sir. Okay. Friction and windage losses really are part of shaft per output. However, in the above calculation, it is not added to the rated shaft output for calculating rotor power input. The error, however, is minor. When a motor is rewound, there is a fair chance that resistance per phase would increase due to winding material quality and losses would be higher. It would be interesting to assess the effect of nominal 10% increase in resistance per phase. Sir, just remember, sir, 10% increase in resistance per phase. Oh, right. We've come to the end, sir. I just wanted to present only one problem that will be giving the whole essence of this particular chapter. But we have to read many things in this chapter, sir. Sorry for the stopgap arrangements I made. Actually, I had one class this morning. I went to headquarters and in this afternoon I took that class. I had no time to prepare the PPT, so I rushed up. Kindly bear with me. Sir, we can interact, sir, now, please. The energy efficiency motor part will be dealt by our SC, sir. Chandrasekaram, SC, will deal the energy efficient part. He's regularly taking classes. Sir, this chapter is particularly useful if one question is asked in the fourth subject. But definitely we'll be getting a question from this chapter in paper 3. That is energy efficiency in electrical utilities. Okay, sir. It will be in future seeing utilization factor measurements, analysis, observations, and all. Star delta mode and all. Capacitor ratings. We have already seen, I think, in chapter 1, sir. Right, sir? Do you remember, sir? Rewinding and its effect on efficiency. Actually, some interesting factors, sir. I'm just reading it from the PDF. The population of rewound motor in India, whole India, or otherwise in some industries exceeds 50% of the total population. The population of rewound motors exceeds 50% of the total population. Careful rewinding can sometimes maintain motor efficiency as previous levels, but in most cases, losses in efficiency will result. Rewinding can affect a number of factors that contribute to deteriorated motor efficiency. Actually, the motor investment is costlier for them, but they do not understand that on the long run, they will be losing much money towards CC charges, current consumption charges. Bureau of Energy Efficiency is giving a wide advertisement for not using rewound motors, but still there is a big industry for rewinding, and the people are still rewinding the motors. It's one important factor. One more thing, that speed control of motors. What is that speed control of motor? We cannot control that motor. N is equal to 120 F by P. What is that? F is a standard frequency available in our grid, and we can use variable speed drive to create our own frequency, and that frequency can be fed to that motor, and by varying that F, we can fine tune the output. That is the speed we can vary with VFT. 120 F by P. In that case, only F is variable that can be varied with the alternate current generators, waveform generators. Okay, sir. Okay. That's all. I think VFT and all we'll be seeing in the next class, sir. I think I covered eddy current devices. This is all fluid coupling. We'll be seeing fluid coupling and all. Soft starter is one more thing, sir. With conventional starters, soft starters are consume less energy, so that the initial shoot up of current will be very much reduced in soft starter. We'll look into it in the second part of the presentation. Okay, sir. I think I covered the core of this chapter. The other parts will be voluminous, but this particular problem is the crux of this chapter. That's what I rushed up and covered it. Okay, sir. Do you want from anything from me? Any clarifications, please? Sir, was it useful, sir?
யூஸ்ஃபுல்லா தான் இருந்ததுங்க சார். பழைய ஏற்கனவே படிச்சதை ரிமைண்ட் பண்ண மாதிரி.
ஓகே ஓகே ஓகே. சரி. ஸோ இதை வச்சு நம்ம ப்ராப்ளம் சால்வ் பண்ணிக்கலாம் இல்லையா? ஸோ உங்களுக்கு ஒரு ஜஸ்ட் ஒரு ஓப்பனிங் கொடுத்துட்டேன்.
கண்டிப்பா சார்.
ப்ளீஸ் ஒர்க் அவுட் பண்ணுங்க சார். பழைய இதுல இருந்து டவுன்லோட் பண்ணி கொஞ்சம் ஒர்க் அவுட் பண்ணீங்கன்னா அது கொஞ்சம் நல்லா இருக்கும். ப்ளீஸ் டோன்ட் ஃபர்கெட். கொஞ்சம் விட்டுட்டீங்கன்னா, இன்னைக்கு விட்டுட்டோம்னா திரும்பவும் மறந்துடும், யோசிக்க வேண்டியிருக்கும். நடுவில் ஏதாவது டவுட் வந்துச்சுன்னா குரூப்ல அப்படியே போடுங்க சார். போட்டிங்கன்னா டக்குன்னு நம்ம திரும்ப பேசலாம் சார். ஒரு இன்டராக்டிவா இருக்கும். எனக்கு இது வரல அது வரல யோசிக்காதீங்க. நம்மள யாரும் தப்பா நினைப்பாங்க, நம்ம தெரியல நினைப்பாங்களா, யோசிக்க வேண்டாம். கொஸ்டின் தாராளமா கேளுங்க ப்ளீஸ். கொஞ்ச நாளைக்கு முன்னாடி என்தால்பி பத்தி பேசிட்டு இருந்தாங்க, ரொம்ப சிவியரா. போடலாம்.
ஓகே சார். ஓகே சார், கண்டிப்பா.
ஓகே ஓகே. முக்கியமா அந்த கிளாஸ் முடிஞ்ச உடனே கேள்வி கேட்டா இன்னும் கொஞ்சம் நல்லா இருக்கும். ஐ மீன் இன்னைக்குன்னா நாளைக்கு போட்டா நல்லா யூஸ்ஃபுல்லா இருக்கும். Otherwise, we'll conclude now. Bala, Dr. Bala is there. Bala குரல் ரொம்ப நாளா கேட்கலையே.
இருக்கு சார்.
இருக்கீங்களா? ரொம்ப அமைதியா இருக்கீங்க குரல் இல்லாம.
இல்லைங்க சார், கிளாஸ் போயிட்டு இருக்கு. 9 மணிக்கு சார் கிளாஸ். ஆக்சுவலா
சாரி, வெரி சாரி. சத்யசீலன் சார் சொல்லி நம்ம மாத்திட்டோம். நான் தான் வந்து அது தப்பு பண்ணிட்டேன். நான் பழைய நினப்பிலே விட்டுட்டேன். அதுலயுமே லேட்டு நான். வெரி சாரி.
அது ஒண்ணும் இல்லைங்க சார். அதாவது இப்போ அந்த கேள்வியை ஏன் இப்போ முன் வைக்கிறேன் அப்படின்னா, நாளைக்கு கிளாஸுக்கு ஆள் இருக்கிறாங்களான்னு கேட்டுட்டோம்னா அவங்களுக்கு தகவலுக்கு சொல்லிடலாம் அப்படின்றதுக்காக.
சார் நாளைக்கு மோஸ்ட்லி கிளாஸ் இருக்காதுன்னு நினைக்கிறேன். ஏன்னா முத்துக்கனி தான் நான் சொல்லியிருந்தேன். அவர் வந்து சாரின்ட்டாரு. அவருக்கு வேற ஏதோ ஒர்க் இருக்குன்ட்டாரு. இப்போ என்னன்னா நாளைக்கும் நான் பாத்தீங்கன்னா ட்ரெயின்ல வந்துட்டு இருப்பேன். அதனால நாளைக்கு வந்து கொஞ்சம் டவுட் தான். அப்படி என்னால முடிஞ்சதுன்னா நான் வந்து கடைசியில நம்ம கவர் பண்ண வேண்டிய சாப்டர் ஒன்று இருக்கு. இந்த எனர்ஜி கன்சர்வேஷன் பில்டிங்ஸ் அது பண்ணிட்டோம்னா ஆல்மோஸ்ட் நம்ம வந்து ஒரு 80% இந்த பர்டிகுலர் சாப்டர்ல நம்ம கவர் பண்ண மாதிரி ஆயிடுவோம். இந்த இதுல நம்ம என்ன எலக்ட்ரிக் சிஸ்டம் ஏற்கனவே கவர் பண்ணிட்டோம். எலக்ட்ரிக்கல் மோட்டார்ஸ் ஃபர்ஸ்ட் பார்ட் இன்னைக்கு முடிச்சாச்சு. கம்ப்ரஸ்ட் ஏர் சிஸ்டம் ஏற்கனவே பார்த்துட்டோம். அடுத்தது HVAC ஒன்று இருக்கு. HVAC பொறுத்த வரைக்கும் நான் வந்து டாக்டர் மேரி எடுக்க சொல்லியிருக்கேன். அவங்க எடுக்கிறேன்னு சொல்லியிருக்காங்க. பம்பிங் சிஸ்டம் இன்னும் கொஞ்சம் ஒரு பார்ட் பண்ணிருக்கோம், இன்னொரு பார்ட் பண்ணணும். கூலிங் டவர்ஸ் ஓரளவுக்கு முடிச்சிட்டோம். நம்ம முத்துக்கணி செகண்ட் பார்ட் எடுக்கிறேன்னு சொல்லிட்டாரு. டீசல் அண்ட் நேச்சுரல் கேஸ் பவர் ஸ்டேஷன் பண்ணிட்டோம். அப்புறம் லைட்டிங் சிஸ்டம் ஒன்று இருக்கு. லைட்டிங் சிஸ்டம் வந்து அது ஒரு 1 day தேவைப்படும். எனர்ஜி கன்சர்வேஷன் இன் பில்டிங்ஸ் இது முடிச்சோம்னா 10 சாப்டர் முடிஞ்சு போயிடுது சார். இதை வந்து நம்ம கொஞ்சம் எனக்கு இன்னும் இந்த மந்த்துக்குள்ள இதை வந்து கவர் பண்ணணும்னு தோணுது. எனக்கு முடிச்சா நல்லா இருக்கும்.
பாண்டியன் சார் கூட HVAC-ல ஒரு பகுதி எடுக்கிறேன்னு சொல்லியிருந்தாங்க.
ஓகே.
அவங்களும் இருப்பாங்க சார். இப்போ இதுக்கு ஓவராலா டிஸ்கஸ் பண்ணணும்னா நாளைக்கு கூட இந்த மீன் டைம் நீங்க வர்றதுக்கு உள்ளார டிஸ்கஸ் பண்ணணும்னா பண்ணிக்கலாம். 9 o'clock இருந்து ஸ்டார்ட் பண்ணா
ஓகே
வேணும்னா. அப்படி இல்லாட்டின்னா கொஞ்சம் லெஷரா விட்டுட்டு ப்ரிப்பரேஷன் பண்ணிட்டு நாளைக்கே பாத்துக்கலாம்னா நீங்களும் ஆராம்சே வரலாம். ஒன்னும் பிரச்சனை இருக்காதுன்னு தான் நினைக்கிறேன்.
சரி சரி சரி
அப்படியே பாத்துக்கலாம். நாளைக்கு ஃப்ரீயா விட்டுறலாம் சார். எல்லாம் மேத்தமெட்டிக்ஸ் எல்லாம் போட்டு டவுட் ஹேண்ட்ஃபுல் ஆஃப் டவுட்ஸோட வரலாம். வந்துட்டு நாளே பார்த்து ஆர்வமா யாராவது கிளாஸ் எடுக்கிறதுக்கு ஆர்வமா வராங்களான்னு வேணா பாத்துக்கலாம்.
சரி. முத்துக்கணி தான் ரொம்ப ப்ராமிசிங் ஃபேக்கல்டி நமக்கு. அவர் வந்து நாளைக்கு கொஞ்சம் இது பண்ணிட்டாரு. நடுவில் இந்த நம்ம ஒருத்தர் ஆனந்தகுமார் எங்க போனான்னு தெரியல. அவர் கொஞ்சம் தேடணும் போல இருக்கு.
அது வாய்ப்புகள் இல்லைங்க சார். அதுதான் நான் அப்பயே சொல்லிட்டேனே.
சரி சரி. நான் பால் கிட்ட பேசிடணும். இன்னைக்கு கண்டிப்பா நாளைக்கு காலையில் நான் கண்டிப்பா பேசுறேன். சாரி, வெரி சாரி, இன்னைக்கு பேசலாம்.
ஓகேங்க சார், பாத்துலாம் சார்.
தேங்க்யூ
தேங்க்யூ சார்.